Hello, y'all. This is Darrell Lee Berry Jr. back with some more linear algebra. I was out for a few days, had a triple week of classes in between, a transition between my early summer classes and late summer classes. I'll make a video about some of the experiments I did in my modern physics lab, so look forward to that within a few weeks or so. For now, let's prepare for some a linear algebra exam that's coming next week. So I'll be starting in chapter 3, section 4, dimensions and its consequences, and I'll be sort of going through the different sections and propositions and so forth that are highlighted. And perhaps next week on Monday or Tuesday, I'll end up working around to doing some problem reviews. So first, let's go to the book. So this is the chapter here. It says once we realize that every subspace V in Rn has some bases, we are confronted with the problem that it has many bases. For example, proposition 3.4 gives us a way of finding zillions of bases and for Rn. As we shall now see, all bases for a given subspace have one thing in common. They all consist of the same number of elements, right? So it's saying that whatever the subspace is, if it's an Rn, then every basis will have n elements to span that space, which makes sense. To establish this, we begin by proving an appropriate generalization of exercise 3.315. So this is proposition 4.1. Let V in Rn be a subspace and let this series of vectors be a basis for B. If L is greater than K, and W1 to WL is in V, then W1, WL must be linearly independent. To be linearly dependent. That makes sense. Because if you have three, let's say you're in R3, so you have your Z, your X, your Y, but you have a space that has four vectors. Since that space is limited to only three, I'm not sure what the best word is, three axes, then you know that at least two of these must equal each other in order for them to span that space, because there's only three axes to span. So two of these must be linear combinations of each other, which makes them linearly dependent. So they gave a proof each vector v can be written uniquely as a linear combination of these. So let's write each vector in W as such. So they're simply showing that WL KL For the jth column of KL matrix consists of the coordinates of the vector Wj with respect to the bases. You can write makes sense. So it seems more sensible intuitively than all of the mathematical jargon. But we just know that since there's more dimensions in the space than there are vectors, excuse me, more vectors than there are dimensions in the space, and at least two of those dimensions must be linearly dependent. And that's why, since they're linearly dependent, then you could zero one of them out. So that's why they're saying you'll end up with a zero vector, because two of these rows will be the same, and you can do this row minus the row above it. So the bottom row is going to be zero, and that's how we know that they're linearly dependent. If you have a zero row, linearly dependent. So let's see what they're saying here. Since L is greater than K, it cannot be a pivot in every column, like we were just saying. So this is a non-zero vector C satisfying. So that row equals zero. So I think they're saying that they're taking that entire row and making it a matrix. This is, we have found a non-trivial linear combination C1W1 to CLWL equals zero, which means that W1 to WL is linearly dependent as was claimed. So I'm not getting the A part. So we know that L is greater than K. So this last L row here, so you got to get used to their notation. So we know the matrix that is multiplying it into has K number of columns, which only has L number of rows. Which is more rows than columns. That's why we end up with that zero row, at least one zero row. Sometimes I think the people who write these books just write certain things just to like look cool with the stuff they're writing. So W is in V. So W can be written as a linear combination of V since it's in the space V. But there's an extra W. So the matrix is the matrix that turns V into W since W is in the space. Now I'm not clear why the entire row would be 0, but I don't want to get hung up on that. Let me make sure I don't overlook something, a specific focus point. All right, so let's look at the definition of a dimension more closely. So dimension right? It says the dimension of a subspace V in Rn, a subspace of Rn, is the number of vectors in any basis for V. We denote the dimension of V dimension of V is defined as dim V. We denote the dimension of V by dim V. By convention, the dimension of the zero vector equals 0, right? So we'll take a close look at example 1. So proposition 4.1, the if a vector in V has more components than the number of the subspaces, it must be linearly dependent. And that's proposition 4.1. Uh, example 1 is coming up. This is proposition 4.2. Before we do the example, which says that V be a subspace of Rn and that V1 dot Vk and W1 WL be two bases for V. So if V is a subspace, and both V through K and V and W through L are two bases, then K equals L. So if it's a basis, then they have to be linearly independent and span the space by definition. So therefore, K has to equal L. And he says this is the numerical analog for a common practice of proving two sets are equal by showing that each is a subset of the other. Here we show two numbers are equal by showing that each is less than or equal to the other. Okay, so let's work through example 1. By virtue of exception of example 6 in section 3, the dimension of Rn is itself n. A line through the origin is a one-dimensional subspace, and a plane through the origin is a two-dimensional subspace. Well, that was a short example. That was theorem 4.2, by the way. As we shall see in our applications, dimension is a powerful tool. Here's the first instance. So we have proposition 4.3. So we're supposing V and W are subspaces of Rn with the property that W is in V if dimension V equals dimension W, then V equals W. So suppose V and W are subspaces of Rn, but the property that W is a subspace of V, but both V and W are subspaces of Rn, the dimension of V, if the dimension of V equals the dimension of W, then they have to be the same subspace. All right? Dimensions are equal. One is a subspace of the other. Should have to be the same subspace. So let dimensions W equals K, and let V1 through Vk be a basis. For W, if W is not in V, then there must be a vector V in V with V not in W. Okay, that makes sense. So if W is not in V, then there's something that is in V that is not in W. Because if everything in V was in W, then it would be the same space. In proposition 3.2, I did a proof by contradiction. Right? So I have to get used to proofs. Right? Let's look at example 2. So it says, let V equals span V1, V2, V3, V4, and that's in R3, where V1 equals 1, 1, 2, V2 equals 2, 2, 4, and V3 equals 0, 1, 1, and V4 equals 3, 4, 7. We would like to determine whether some subset V1, V2, V3, V4 gives a basis for V. Of course, this set of 4 vectors must be linearly dependent since V is in R3 and R3 is only 3-dimensional. That makes sense. Now let's examine the solutions of, okay? So for linearly dependence, what they're saying is in order for it to be linearly independent, C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equals 0 can only be true if all the C's are 0, if they're linearly uh, uh, independent. Since they must be dependent, at least two must depend on each other. So one can be positive and one can be negative versions of the same one. And thus, for instance, these C's here can be something other than 0, but still 0 out the whole thing. So this could be 0, this could be 0, but these can be positive and negative 1, for instance. And since V's are linear multiples of each other, you can make them equal, and then they'll 0 out. So you're solving the matrix for 0, and as we can see, we do get a 0 row, which shows that it's linearly dependent. So V2 and V4 can be expressed as linear combinations of V1 and V3. So V2, both V2 and V3, because basically looking at this equation here, if we solved for V2, then V2 is in terms of V1, and if we solve for V4, then V4 is in terms of V1 and V3. But V1 and V3 are linearly independent because they have pivots. So as you can see, they have pivots, so they're independent, but uh, the third column and the fourth column don't have pivots, so they're dependent. So V1 has a pivot, it's independent. V3 has a pivot, it's independent. But you can make one vector basically out of V2 and V4. Because if I make V2, if I make V1 1 half V2, and I can put that into the V1, and 4 is dependent on those, but it's its own vector. So it's saying the subset. So that's the difference here. It's not saying whether these 4 are bases, all 4 or not. But you can find a subset that could be a basis, because these 3 are independent. But 2 and 4 are dependent, but still are independent of V1 and V3. Right? Let's see what else we have here. We just looked at example 2. Let's find theorem 4.6. So it looks like a prominent theorem. I just passed it. That's theorem 4.5. All right, here we go here. Okay, so I looked at this before. Theorem 4.6. Dimensions of the row space of A equals the dimensions of the column space of A equals R. Dimensions of the null space of A equals n minus R. And the dimensions of the A transpose of the left null space is m minus R. So I think what I'll do is stop here, and I have a better understanding of these 4 spaces. So what I'll do is come in the next video I make, will start here, and we'll do an example of these 4 spaces so we can sort of prove this. So that's what we'll start next time. So I'll come back in a few minutes, and I'll take like a 10-15 minute break, and then we'll come and show that this proposition 4.6 is true by actually making an example of the row space, null space, column space, and left null space. And we'll see how that works. So, like, subscribe, share if you haven't. Help me get to 1,000 subscribers by December. I'll be back in about 10 or 15 minutes, and we'll use an example vector to get the 4 fundamental subspaces and then see if this theorem holds out. See you soon.